Hello everyone. This is Swati from Aeronautical Engineering. Today we are here for the seminar topic of synthesis of the aerodynamic model of a flying wing aircraft. So, introduction to flying wing aircraft. Flying wing aircraft are unique because they have no distinct fuselage or tail section. The entire body functions as a wing, providing lift across the whole structure. The design offers benefits like reduced drag and better fuel efficiency, but also brings challenges in stability and control. To analyze and design such aircraft, engineers must create accurate aerodynamic models. These models help predict how the aircraft will behave in flight and allow the better control system design. Synthesizing such models involves integrating theories, simulations, and experimental into an undefined representation of aerodynamic behavior. Importance of aerodynamic modeling. Aerodynamic modeling is essential to understand how airflow over a flying wing aircraft and how it affects its motion since the flying wing lacks vertical and horizontal stabilization. Traditional modeling approaches used for conventional aircraft may not apply. Engineers need a special aerodynamic model that consider lift, drag, pitching moment, and side force specific of the configuration. Without accurate modeling, stability analysis and control system development would be faulty. Therefore, synthesizing a reliable aerodynamic model is the foundation of ensuring the safe and efficient performances of flying wing aircraft. Challenges in flying wing stability. One of the main difficulty in designing flying wing aircraft is achieving longitudinal and directional stability. Unlike conventional aircraft, flying wings do not have a tail to counteract pitching and yawing movement. As a result, their natural aerodynamic stability is lower. Small challenges and angle of attack can be lead to a large shift in pitching moment. The aerodynamic model must carefully account for these sensitivities to predict how the aircraft reacts to disturbances. Understanding these stability issues is crucial to build effective flight control system and prevent potential in-flight instability. Role of computational fluid dynamics. Computational fluid dynamics is a powerful tool used to simulate airflow over the surface of the flying wing, helps engineers understand how different shapes and angles affect the lift and drag in the synthesis of aerodynamic models. CFD provides data that cannot able to be obtained from wind tunnel testing alone. Engineers simulate different flight conditions such as cruise, climb, or turn and observe pressures, distribution, vortices, and flow separation. These simulations give critical input for constructing accurate aerodynamic coefficients that go into the final model of the aircraft. Wind tunnel testing and validations. Despite the power of simulation, wind tunnel testing remains essential in aerodynamic model development. Scale models of the flying wing are tested in wind tunnels and gather real-world aerodynamic data. Measurements of forces and moments under controlled conditions help validate CFD prediction and correct any disciplinaries that these results are used to find the aerodynamic model that can make more accurate. Wind tunnel testing also provides insight into nonlinear behavior such as stalls and vortex breakdown, which are difficult to capture purely through simulations. Lift and drag characteristic. This synthesis of aerodynamic model begins by understanding the basic forces acting on the aircraft lift drag flying wing because lift across the entire structure which make them the more efficient that traditional aircraft. However, air drag characteristics are more complex due to blending of the body and wing. Engineers must analyze how the design affect the lift to drag ratio, especially at the different speed and angle of attack. These relationships are captured using aerodynamic coefficients, which are critical components of the final model. Pitching moment and trim condition. Pitching moment refers to the rotational forces around the aircraft lateral axis in flying wing aircraft. Managing this movement is challenging due to the absence of a tail plan. The aerodynamic model must accurately describe how pitching movements changes and with angle of attack and speed trim conditions, where the aircraft maintains steady level flight and analyzes the balancing lift and pitching moment. If the pitching moment is not controlled, the aircraft can become unstable. Proper modeling in the behavior is essential for achieving pitch stability and designing appropriate control system. Yaw stability and lateral control. Since flying wings typically lack vertical stabilizers to maintain yaw stability is difficult. Yaw refers to the rotation of the aircraft about its vertical axis. The aerodynamic model must account for side forces and yawing moments created by the asymmetrical airflow or control inputs to improve lateral control. Engineers often use split drag rudders of differential thrust. The aerodynamic model must include these mechanisms and predict how they influences your behavior. This helps design effective control strategies and maintain directional stability during turns or turbulence. Roll behavior and control surfaces. Rolling motion or rotation around the longitudinal axis is another key part of aircraft dynamics. Flying wings use ailerons, a combination of elevator and ailerons, to control both pitch and roll. The aerodynamic model needs to describe how control surfaces deflection produce a rolling moment. Since ailerons are located near to the wingtips, their effect varies with speed and angle of attack. The model should capture this non-linear effects to ensure accurate predictions during maneuver. Understanding role behavior is essential for safe turning and coordinate flight. Nonlinear effects in aerodynamic modeling. Unlike traditional aircraft, flying wings are more prone to nonlinear aerodynamics behavior. This includes flow separation, vortex formation, and rapid changes in lift and movement at high speed, high angle of attack. The aerodynamic model must account for such nonlinearities, especially in extreme flight conditions. Simplified linear models may not be sufficient, and for control design, these cases, engineers often use high order polynomial fits or lookup table based on CFD or wind tunnel data. Accurately modeling those nonlinear effects ensures that the aircraft responds correctly to control input. Control surface modeling. Control surfaces play a critical role in managing the aircraft's orientations and stability. In flying wing aircraft, uh, ailerons on drag rudders are primary control devices. The aerodynamic model must define how the deflection of the surface affects aerodynamic forces and moments. These relationships are captured using control derivatives, which are functions of speed, angle of attack, and surface deflection. Modeling control surface accuracy is essential for design flight control system that can stabilize the aircraft in various flight remains and under distribution. Parameters identification techniques. To build an accurate aerodynamic model, engineers use to identify various parameters such as lift, curve, slope, drag, coefficients, and control effectiveness. These are often determined using systems identification techniques. This involves exciting the aircraft or model through no inputs and measuring these outputs are using algorithms to estimate the aerodynamic parameters. This process is often repeated for multiple flight conditions. The identified parameter are they used to construct the comparative model that captures the dynamic of the flying wing across wide operating envelope. Integrating the flight dynamics model. Once the aerodynamic model is synthesized, it is integrated with the aircraft flight dynamics model. That combined model describes how the aircraft will behave in response to control inputs and external forces. Engineers use this simulate flight behavior, access stability margins, and design air autopilot systems for flying wings where natural stability is limited. This integration is especially important. Control laws must be designed to ensure that the aircraft remains controllable and responsive at the phase of flight from takeoff to landing. Simulation and validation of the model. Aircraft the After the aerodynamic model is completed, it is used to flight simulation to test different sensories. This includes normal flight turbulence, such sudden control inputs and failure conditions. The model predictions are compared with experimental data and or actual flight testing results if available. If the prediction match well, the model is considered validated. If not, the model is refined further. This interactive processes ensure that the final aerodynamic model is both reliable and accurate, forming a solid basis for control system design and performance evaluation. Conclusion and future work. This synthesizes of the aerodynamic model for a flying wing aircraft is a complex but essential process. It involves a detailed understanding to lift, drag, moment, control surface, nonlinear behavior. Accurate modeling is crucial for ensuring stability, control, and performances. As further work, more advanced modeling techniques like machine learning based aerodynamic estimation or real time system identification may enhance predictions accuracy, improve CFD, and experimental methods will also help refine models. Ultimately, these effects support the safe and efficient operation of flying wing aircraft in both military and civil aviations. Thank you.